I guess we are ready to start. Thank you everybody for coming back to the afternoon session. So we start this session of the short talks with the talk by Caio Bueno, who will tell us everything we need to know about modified character sums over the k-free integers.
So first of all, thank you for the introduction, and thank everyone for attending the seminar. I'll talk a little about modification of the Dirichlet characters and sums of these functions over the k-free integers. So let's start with some definitions. A few of them we have already been seen yesterday. And we say that a function is multiplicative if for any natural numbers coprime to each other, f m times n equals fm times fn. And it is completely multiplicative if this is valid without restriction, without the coprimality. We also say that a positive integer is a k-free integer if there is no prime p to the power k that divides this number. And finally, we have that a function has support on the k-free integers if it vanishes outside of the set of k-free integers. So for example, the classical Möbius function is multiplicative and by definition support on the square-free integers. So consider the k-free set. We are interested in the following question. For which values alpha greater than 0, can we find a multiplicative function that satisfies those hypotheses? F has support on the k-free integers. At prime numbers, it takes values plus or minus 1, and its partial sums oscillates at most like x to the power alpha. So before discussing this, let's try to motivate why we are asking this question. And in 1957, Erdős presented a conjecture, the Erdős discrepancy problem. And he asked if for any function, any arithmetic function, that goes from the naturals to plus or minus 1, if the supremum is uniformly bounded by some constant, or if it is infinite. And half a century later, tau, this became a theorem by Tau, and he proved that this supremum is in fact infinite. Okay. So an important function that we have is the Dirichlet character, and it has the following properties. It is completely multiplicative, a Dirichlet character modulo Q. Here I'm taking a quadratic character. It is Q periodic. Period is its modulus, and it assumes values plus or minus 1 if a prime number does not divide its modulus and 0 otherwise. So the Dirichlet character, it's what we call an extreme example to the Erdős discrepancy problem, or a near counterexample, because if you consider a Dirichlet character modulo Q, as above, since it is completely multiplicative, we have the first equality, and the second equality comes from the fact that a Dirichlet character is bounded by 1, the first inequality, and the second inequality is the Polya-Vinogradov bound. Trivially would be bounded by Q, so we have a finite discrepancy for a Dirichlet character. But of course, it's not a real counterexample since it vanishes for a finite subset of prime numbers. But this is interesting because we have an example where it is a non-trivial example of a function that has finite discrepancy, and it is it almost satisfies the Erdős discrepancy problem. We have that it vanishes only for a finite subset of primes. Another important example is what we call the modified Dirichlet characters. And we define as follows. We take a quadratic Dirichlet character modulo Q, and we define G sub index chi as equals to the quadratic character if a prime number does not divide its modulus and one otherwise. So it's probably the simplest modification we can do to eliminate the zeros of a Dirichlet character. And of course, by the Erdős discrepancy problem, this has unbounded partial sums. And in 2010, before the solution of the EDP, Boran, Choi, and Kunz presented the following example. They considered the Dirichlet character modulo 3 and set the modified character as follows, as we did earlier. And they showed that its partial sums is big O of log x. So we have a completely multiplicative function that has logarithmic cancellation. Okay. So in fact, when we look at the proof of the Erdős discrepancy problem, it is reduced to the case where we consider only completely multiplicative functions that pretends to be a Dirichlet character in some sense, in the sense of pretentious theory. So again, our question is, can we find example of multiplicative functions supporting the k-free integers? At prime numbers, it is equal to plus or minus 1, and its partial sums are big O of x to the power alpha, and we want to look for small alphas. Okay? So it is natural to look first at functions that looks like Dirichlet characters. Okay? So a little bit of the results that we have up until now. Remember the definition of a modified character. It is equal to a Dirichlet character, a real Dirichlet character, when a prime number does not divide its modulus. Okay? Here, m to the k, it is equal to the characteristic function of the k-free integers. If n is k-free 0 or the so this is just a characteristic function for the k-free integers. And in 2020, Imon showed that for the square-free integers, if you consider the modified character, we have cancellation of the order x to the power 2/5, assuming the Riemann hypothesis plus an epsilon. And unconditionally, this cancellation is square root of x times this exponential. Later, this result was generalized to the k-free integers by Raimoni, Medeiros, and me. We proved that for the k-free integers, this cancellation is x to the power 1 over k plus 1/2 plus epsilon, assuming the generalized Riemann hypothesis. And this is in agreement with the previous result in the case where k equals to 2. And unconditionally, this has cancellation of x to the power 1 over k times the same exponential. In 2023, Liu improved the previous result and showed that for square-free integers, it is x to the power 1/3, assuming the Riemann hypothesis. And she also improved the unconditional bound. This exponential was improved, but we have no power saving on the main term. Basically, he used the Vinogradov-Korobov zero-free region for the unconditional result, and we used the simplest zero-free region. I built upon Liu's work to generalize this result to the k-free integers. And the main result is the following. We consider a quadratic Dirichlet character chi modulo q, define f as the modified character restricted to the k-free integers, and under the Riemann hypothesis, these partial sums oscillates at most as x to the power 1 over k plus 1 plus epsilon. And here, I'm interested in these partial sums in terms of x, not on the modulus of the character. Okay. So I will present just the basic idea for the proof. The first part, we just define the the Dirichlet series of F as Fs, and by the Euler product formula, we can see that it is equal to the product of these three Dirichlet series in the even case, and this four Dirichlet series in the odd case, where P is just this finite product. So talking now a little about the even case, the first part of the proof is to split the sum, the partial sums in the following way. We define H to be the coefficients of the Dirichlet series PS over zeta Ks. And this first partial sum here is a bit easier to bound. So we need a bit more work to show this second partial sums when we restrict A to be greater than Y. Okay. So the second part of the proof involves this proposition that it is a bound for the tail of this Dirichlet series, and we assume the Riemann hypothesis. We have that for in the half plane sigma greater than 1 over k plus epsilon, that this tail is big O of y to the power 1 over 2k minus sigma, that's the real part of S, plus epsilon. And we use the Perron formula to prove this in the usual way. We change the contour and estimate each line segment using complex analysis. We also need a bound for the second moment of the Dirichlet L function that we apply to estimate the vertical line segment when we change the contour of integration. So we combine the last proposition and this lemma to prove that this partial sum is in fact x to the power 1 over k plus epsilon. 1 over k plus 1 plus epsilon. And a few informations we have. If you define that s to the power kx to be the number of k-free integers up to x, we have this result from Montgomery and Wagner under the Riemann hypothesis that the set is x over zeta k plus an error term, and this error term is exactly what we have in our theorem. This has seen some improvement by a little margin, but so our result is exactly this error term. And for this error term, it's conjectured that it is actually x to the power over 1 over 2k. Okay. Also, the product of the Dirichlet series that we obtain for our function f, assuming the Riemann hypothesis, and the Riemann hypothesis for our functions is analytic in the half plane in the half plane to the right of 1 over 2k. So we conjecture that the real magnitude of these partial sums are actually x to the power 1 over 2k plus epsilon, assuming the Riemann hypothesis. But only these facts are not enough to ensure this type of cancellations. Okay, so, but we still could have room to improve a power saving. Okay. And this is